Welcome to The Explainer. Today, we're diving into what is literally the engine of the future, powering our modern world in ways we honestly take for granted all the time. Whenever you flip a switch, charge your phone, or see these massive industries operating around the clock, there's a highly calibrated scientific process making it all happen behind the scenes. We're going to demystify the heart of the nuclear power plant. It's a journey that'll take us all the way from the invisible structure of an atom right up to our massive national energy grids. Let's get into it.
So, let's establish the big picture right out of the gate. When we talk about nuclear energy, we're really talking about an absolute cornerstone of our modern infrastructure. It's one of the largest sources of reliable, affordable, and secure electricity we have today. Unlike some other clean power sources that might dip depending on the weather or if it's nighttime, nuclear reactors are built to run continuously. They provide this incredibly stable, highly efficient baseline of power. That specific baseload is a total engineering marvel, and it's absolutely crucial for maintaining our energy security and keeping the economy running without a hitch.
To really wrap our heads around the sheer scale of this technology, just look at this number, 94. That's 94 commercial nuclear reactors operating right now just in the United States alone. And if we look worldwide, there are over 400 commercial reactors actively generating power. When you think about the unbelievable volume of electricity it takes to sustain modern civilization, that number really hits home how heavily we rely on this technology every single day. Here is our roadmap for today. First, reliable, affordable, secure power. Second, splitting atoms, nuclear fission. Third, inside the reactor core. Fourth, pressurized water reactors. Fifth, boiling water reactors. And finally, powering innovation and security.
All right, Section 1, reliable, affordable, secure power, the big picture.
Moving right along to Section 2, splitting atoms, nuclear fission.
Okay, to really understand those macro benefits we mentioned, we have to zoom way down to the microscopic level. The absolute crucial piece of the puzzle here is fission. Fission is a physical process where atoms actually split apart, and in that precise moment of separation, they release a tremendous amount of energy in the form of heat. Honestly, you can think of the entire massive structure of a power plant as basically just an ultra-secure, highly engineered housing unit built for one specific purpose, to safely manage and sustain this tiny invisible chain reaction.
Which brings us to Section 3, inside the reactor core.
Now that we know what fission is, how do we mechanically harness all that tremendous energy? Well, it all starts with the fuel itself. Reactors use uranium, but it doesn't just get tossed in there. The uranium is actually carefully processed into these small ceramic pellets. Those little pellets are then stacked end to end and sealed inside metal tubes, which we call fuel rods. Then you take over 200 of these individual rods and bundle them together to form a single fuel assembly. Finally, a typical reactor core is packed with a couple hundred of these massive assemblies, depending on how much power is needed. It's really just an incredible feat of dense, efficient engineering.
Inside the reactor vessel, all those fuel assemblies are completely submerged in water. And this is just a genius piece of design because the water serves an incredible dual purpose. First, it acts as a coolant, absorbing the intense heat generated by those splitting atoms. Second, it acts as what we call a moderator. This means the water actually helps slow down the neutrons produced by the fission process, which you absolutely need to do to sustain the chain reaction. Plus, operators have control rods they can precisely insert or withdraw from the core. Drop them in, the reaction slows down. Pull them out, it speeds up. It gives us total, precise control over the energy output. Despite all the mind-bending physics happening at the atomic level, the actual mechanical output is beautifully simple. It's basically a giant, super-advanced kettle. First, the fission creates immense heat. Next, that heat turns water into steam. Then, the intense pressure of that expanding steam spins a massive turbine. And finally, that spinning turbine drives an electric generator to create the electricity that powers your home. It's literally just a highly secure, high-tech way to boil water.
Let's look at Section 4, pressurized water reactors, or PWRs.
Zooming back out to the American fleet, every single commercial reactor in the U.S. is what we call a light water reactor, meaning they use regular water to get the job done. But they fall into two main camps. A commanding 65% of them are pressurized water reactors. Roughly a third, about 33%, are boiling water reactors. So, starting with those dominant PWRs, how exactly do they work? Well, they actually pump water into the reactor core under incredibly high pressure. That extreme pressure physically prevents the water from boiling, even though it's absorbing an unbelievable amount of heat from the nuclear fission.
And that leads us right into Section 5, boiling water reactors, or BWRs.
So how do these two systems handle steam generation differently? With the pressurized water reactors we just talked about, that superheated, highly pressurized liquid water is pumped into tubes inside a completely separate heat exchanger. Those hot tubes then boil a secondary water source to create the steam that turns the turbine, while the core water just safely cycles back. Boiling water reactors, on the other hand, skip that secondary loop entirely. BWRs let the water heat up and produce steam directly inside the reactor vessel itself, and pipes feed that steam straight to the turbine. In both systems, though, the unused steam is condensed back into water and infinitely reused in this beautifully efficient loop.
Finally, Section 6, Powering Innovation and Security.
Zooming all the way back out from the nuts and bolts, let's talk about what this continuous, highly efficient power generation means for the bigger picture. This massive, 24/7 power output directly supports the critical goals of the Department of Energy. By maintaining this robust fleet, we're ensuring absolutely dependable energy delivery across the nation, which prevents blackouts and keeps prices stable. But beyond that, we're driving energy innovation, using these reliable baselines to help fund and research the technological systems of tomorrow. And crucially, a strong commercial nuclear sector goes hand in hand with maintaining vital nuclear security in our national defense infrastructure. The stability of one literally guarantees the strength of the other. So this leaves us with a really fascinating question. How will nuclear innovation shape our energy future? As we look toward a world that demands more and more electricity, yet is constantly striving for clean, reliable sources, understanding the atomic engine at the heart of our grid has absolutely never been more important. What does having continuous, secure power mean for our collective tomorrow? I'm going to leave you pondering that incredibly vital foundation. Thanks for joining me on this explainer, and keep questioning the incredible world around you.